transform the eigenvalues from A to the eigenvalues of ACL, which is A minus BK, right? How do you do that? You feedback the states through a constant gain feedback vector K. So basically, this is the block diagram, right? This. Okay, so obviously from here, alright, you only feedback states. You have a copy, alright? What you need to do now is, let's say you want a reference input. Okay, so you want to, instead of Y following U, you want to follow a reference input. So in obvious way, to introduce a reference input is to change the control law. So U has been minus AX plus R. Alright? This will result in a non-zero steady state error to the input. Okay, so how the question is, how do you achieve start, how to achieve YSS equals to R? Okay, this came out in last year's exam. Will it come out again? I don't know. Okay, how to achieve this state? Output equals to reference input R. Alright, the desired steady state output to the reference input is YSS equals to R. So if you want the steady state output to be R, you look at everything in steady state. Okay? So corresponding steady state. Alright, with this. So remember x dot is x dot SS. A steady state, the rate of change of your states should be 0. So 0 equals to AXSS plus BUSS. Steady state output 1SS, you want it to be RSS. Okay? Which is CXSS plus BUSS. Alright, next we say that XSS, alright, will contain somehow the reference input RSS. So XSS is a vector, and next RSS, and input USS is a vector, and U RSS. Okay, and you put these two in here, you form A and X RSS plus B and U RSS equals to 0. C and X RSS plus D and U RSS equals to RSS. Alright, then you simplify these two equations. First equation, you factor out RSS. Okay, so you have A and X plus B and U in brackets times RSS equals to 0. And this is not existent. Because that equals to 0 or this equals to 0. Second equation, factor out RSS, so C and X plus D and U bracket RSS equals to RSS. Cancel, C and X plus D and U equals to 1. Okay, so these two equations, A and X plus D and U equals to 0, C and X plus D and U equals to 1. So I've been talking to myself. Okay, again, first equation, we factor out RSS. Okay, so bracket AX MX plus BNU times RSS equals 0. Something times something equals to 0. This is a scalar, RSS is a big number, so cancel. No more. Second equation, factor out RSS, so CNX plus BNU plus RSS equals RSS. Cancel, 1. Okay, so there are only two equations now. ANX plus BNU equals 0, CNX plus BNU equals 1. Put them into matrix format. So A, B, C, D here, NX and U. So A times NX plus B times NU equals to 0. C times NX plus B times NU equals to 1. Okay? So from here you get this. Understand? Yes? From these two equations, you get this. Is this okay? Yeah. Next. You know the relationships now for y-axis equals to r. So how are you going to implement this? The way to implement this is the next page. What you wish to do now, you can read from here, but it's very short, so write down that what you are trying to do now is you are trying to have u. Is this your next page? Oh, sorry, which is the next page? This one, eh? Is it this one? Yeah. Sorry. Sorry, yeah? Okay. So now, you have this. You shift A, B, C, D to the right hand side. Okay? So you can identify NX and NU. Step 1. So NX and NU is shift A, B, C, D to the right hand side, like this. Alright? Step 2. How is this related to a control signal? Okay? So, write down this. U equals to minus kx, yeah? So USS is minus kxss. U minus USS is minus k bracket x minus xss. Okay? Alright, next step, you move this USS to the right hand side. You don't need to copy this for time being. Follow me. Alright? So write down this one first. Okay? U equals to minus kx, USS is minus kxs. This one minus this one. Next, you move USS to the right hand side. And you get this one, number 2. U equals to USS minus K, X minus XSS. Okay? And all of you see how you get this? Yes? Alright? Any questions? Just raise up. For the two of you, check your friends. Okay. Then, next. You'll try to put your USS and XSS into the format just now. So USS is NU RSS. XSS is NX RSS. Remember? Don't remember. The previous slide. This is this, and this is this. Okay? So you substitute. USS is NU RSS. XSS is NX RSS. Okay, basically what we're saying is that steady state control signal as some component of the reference. The steady state as some component of the reference. Okay? We group RSS together, so minus kx here, plus bracket NU plus KNX, close bracket RSS. Okay, we say that we call this M bar. So U is minus kx plus M bar RSS, and M bar is just NU plus KNX. Now that you have this control input, this will cause your y-axis to tend towards your reference input. Okay, so this is the design for RSS to go to your reference input R. How do you implement this in block diagram? You draw this into this. Okay? So, if you can follow me, what you do is you take NU times R, okay, plus K times NX. So NU times R, here, positive sign, plus Because k, u is minus kx, right? So you want to use the same block, yes? Right now. So you need to multiply by another minus sign. Minus. Okay? So from this part, you take r times nx, so you have nxr. Give you a negative sign, so you have minus nxr times this minus k, you end up with kn xr. Alright? And that goes into your u. And this u is also a part here, that is minus kx. Double stroke because x is a vector. Can everybody follow this? Yes or no? No. Okay, good. No is a good response. Huh? U is minus kx plus nu plus k nx r s. Right? So your input r, okay, times nu. Okay, this will give you NUR. Positive sign. Take R times NX. This will give you NXR. Yeah? And then you need times K, right? Okay? Remember that on this side, U which fits into this, x dot plus bu, ax plus bu. X dot equals to ax plus bu. We give you an x, right? And then this was supposed to give you here minus k. Yes? Instead of drawing it here, now we take this away and draw this here. Minus k. Okay, so this extends all the way here. Yeah? And what do you have here? From this part, you have u equals to, first of all, minus k. Yes? But you still need to add on this part. From the r. How do you add on? So you have nxr. nxr. I need times k, right? Right. So what do you do? Is put in this is with a minus sign. So we have minus nxr times minus k. Minus nxr times minus k is k nxr. Then you plus to this one. So you plus k. You write this one. Because it's not u yet. So this half here, is just minus kx plus k and x r. Okay? So you take this part plus this part. And so you end up with u. Okay? U will be NUR minus kx plus k and x r, which is this. Okay? Alright, and this is this. Okay, so let me just repeat again. You take NU times R here, NX times R, and then put a minus sign, so it's minus NXR times minus K. Later on to this part here. Okay? And then you group NX and NU together. It's called M bar. Alright, what's more important is the question. If there's such a question comes about, what is the gain required for the output to reach reference? You need to recall for a derivation. Okay? So you can repeat everything in front. What is everything in front? Everything in front includes from, before you copy, let me just say this part. Okay? And okay? Finish short, it's 1. Alright? So u is minus k plus nu plus n k and x bracket r, where nx and nu is in short. Alright, but the best is to give us everything. Right? Okay, so can all of you understand how we derive this and this? Alright? Okay? Anybody thinks I'm talking alien language? No? Good. Alright. So in summary, because I already have someone who's like okay, in summary, the overall closed loop description is, u equals to minus kx, so a minus b kx. Okay? In the past, you have ax minus bu, so now it's a minus b kx, because u is minus kx. And then, u other than b minus kx, there's an additional component, m bar r. Right? So it's x naught equals to ax plus b bracket minus kx plus m bar r. Okay, and y equals to cx when b is 0. So you take x naught equals to ax plus b bracket minus kx plus m bar r. You put the x and x together, and now a minus b kx plus b m bar r. Alright? Okay. Where m bar is nu plus a n x. Okay. It's still quite early, it's 3:12. How? Go home and you have one revision lecture shot. You want that? No. You want a break? Huh? No? Yes? Okay, if I continue, I can finish in maybe 40 minutes. Continue? Yes? Alright. I'm also tired. Okay. If you happen to have, or if you have the next and last set of notes, observer design. Okay, here I said I don't want to time myself, I'll go through step by step. Because this is again a very confusing section in state space. Okay, ready? Yes? No? You want to take a 5 minutes break? No? Okay, good. Alright. So this is nothing new, this is controller. Controller design, yes? U is minus kx. Still taking that controller. What is observer design? Okay. So, state feedback is very nice. And by Ackermann's formula, you can easily calculate K. Yes, it's simple. All you need to know is how to form the alpha CA. Alright? From ACL. Okay? So please do remember what it means. Okay, so but the problem is that is that it requires all the states to be measured. Why? Because if you want to specify a control input U is minus kx, you need to know all your x. You need to know x1, x2, all the way to xn. But realistically, you may not know all the states. Okay? Just because, I say in the chemical plant, in the boiler, I think I've said this example before. You are not able to measure certain parameters because it's unsafe to do so. There are no sensors available. So you need a reference from the output. Alright? So for this reason, we introduce the idea of observers. How do you observe the state of the output? Okay, which is the mechanism for estimating the states from available measurements. Alright, sometimes we use the term observer, sometimes we use the term estimator, because the observer is just an estimator. Okay? An open loop observer looks something like this. Alright, the real plant, real, R-E-A-L, real, right? If you have input U, you get Y. Estimated model, you figure the input, put in the input U, you get X hat, which are the estimated states. And C, you get Y hat, which are the estimated, so-called observed output. Alright? The model and the process outputs, Y and Y hat, are only identical if we know all initial conditions and all observations as well. Right? Okay, so now I'm going to do some writing. Alright, I think this is the way. Yes? Real estimated slash research. Alright? Okay, so we are ready for a challenge now. Alright, so this lesson starting from 3 p.m. We are learning about observers. We just finished flow placement. Yeah, and how to introduce our reference method. Okay? So this is a very heavy, intensive lecture. Observers. Estimators. This is what I'm going to design from now on. Alright? Okay? The real process. Okay? You write down as I write down, right? To keep yourself focused that you are designing this now. Alright? The real process is x dot equals to ax t plus b u t. Initial condition equals x naught. Okay, y equals to c x t plus d u t. And usually your d is 0. Okay? Yep. Model. Model is estimated hat. Okay? Equals to A x hat plus B U up to Y C X. That's the model, estimated. Here, you start to define stuff, right? First of all, you want your model to be as close to your real as possible. But is that always true? No. So we define something called x tilde. Okay? X tilde xt minus x hat. Okay, what's the definition of x tilde? X tilde is called state estimation error. Yeah? Error. And x hat is something that we call state estimate. find the state estimation error, x tilde, to be actual state x minus state estimation. Okay. Next, there are dynamics for the state x. So if x dot equals something, right? There are dynamics for the model, the state estimate. So if x hat dot equals something, right? There are dynamics for the state estimation error. Okay? So for error. Okay. Alright. X tilde dot. Because when there's a dot, there's a derivative under the dynamics, right? X tilde dot is x dot minus x hat dot. Okay? So, du got a x minus x hat. Okay? And this is just a x tilde t. Okay? Initial conditions, x tilde 0 is x0 minus x hat 0. So if your initial condition for the rail and the estimate are the same, x tilde 0 is 0. Okay. Alright, what does this mean? Now I need to go through some math. We have got space here. Okay? So what does this mean? Okay, what does this mean? X tilde dot equals to a x tilde. Okay, now we want to go through what is x tilde dot equals to a x tilde t. Alright? Okay, so what I want to tell you now is that the dynamics are decided by the eigenvalues of, any guesses? Huh? You only have one matrix here, A. So the dynamics are decided by the eigenvalues of A. Okay? So example, if eigenvalues of A is minus 0.1 and minus 0.3, very small. Okay, what do you expect x tilde to look like with time? T. Okay, 0. So it will decay very, very slowly. Alright? Versus eigenvalues of A to be minus 100 and minus 300. X tilde T will be the 0. Okay? Alright? Because there's no input, there's no reference, there's nothing. So the only thing you can do is to decay to 0. Okay? Just the only question is whether it decays to 0 very fast or very slow. Yeah? Okay, so as a summary, for stable systems. Okay, what does it mean? Stable systems? To make it easier for you to copy, I say EIGA, eigenvalues of A, negative. Okay, first condition, eigenvalues of A must be negative, otherwise it didn't decay. It will just go this exponential. Yeah? Alright, so what does it mean? This tells you that the closed loop holds negative real parts. Okay? And then error x tilde tends to 0. Okay? So this is the main idea. Alright, so if you want your model, the estimator, to follow your rail, you must make sure that error goes to 0. Once the error tends to 0, your estimator model and the estimated output y hat is no different from 1. Okay? That's the main idea for designing our estimators. Alright, so this is whatever you have just copied and understood in the past 10 minutes. This slide and this slide. Okay, so let's look at this slide. Basically, we say that error x tilde is x minus x hat, state minus estimate, you want it to 0. When you want x tilde to 0. So when x tilde tends to 0, the state x is your state estimate, x hat. Okay, so we said error will definitely converge to 0 for stable systems. So what are stable systems? Stable systems are if your state matrix A is stable, meaning the eigenvalues are negative. Okay? But you cannot influence the rate at which it converges to 0. So it's converging to 0 at the same rate as the natural dynamics A, which may not be satisfactory. So how do you force your state estimation error to go to 0 faster? That's the question. You don't want to rely on A, because A may have eigenvalues minus 0.1, minus 0.3. That's going to take forever. A not good enough. You want to force it to go to 0 faster so your state is immediately stable. Alright? So in trouble, use feedback. So what feedback are we going to do? Are we going to use? We are going to use okay. Process, model, real estimate, real state, estimated state, real output, estimated output. Alright? So real output minus the estimated output. Error. Okay, U, take this error, pass it through a feedback vector, back to your model. Okay, how does it work? Okay, so to keep your brain operational, let's do some more copying. Alright? So you want this. Okay, you want this. Alright, but if you fit L back to your model will have an additional input. Yes? Now what is this additional input? This additional input is called L mu. Okay? L mu. Mu, the B, curly B. You want to call it B? It's not B, it's curly. It's a Greek symbol. No? Okay, you want me to call it B? I call it B. Okay? Understand it's curly. B, B, you want a B. Doesn't matter anyway. Don't say that I said that. Okay, so your model X hat. Maybe just before you go and stare at me, right now. X hat dot is supposed to be A X hat plus BU. Yes? Because initially there only one input U1. Now there's an additional input. Alright? The additional input is called L mu. Or you want to call it B. Like that. Y hat, still C. Okay, fine. Alright? Okay, there's some more space at the bottom of the slide. So if you write really, really small, you can fit in what I'm going to write later. Alright? Done? Okay? Let me take this away. Piece of black paper. Or you can just, I just said, write really, really small. You can fit this at the bottom of the slide, alright? Okay, this you do not have to copy. The first three sentences I don't copy. Mu is defined as yt minus y hat t. Yes, it's an error. Alright, this thing you don't have to copy because you have already written down. X hat dot is A X hat plus BU plus L mu. 1. Y hat is C x hat. Okay. Alright? So from 1, for the model, x hat dot is A x hat plus this one, new one, is y minus y hat. Okay? So in case you cannot follow me, let me just write down L y minus y. Okay? What is y minus y hat? Cx minus cx hat, right? L C x minus x. Okay, the real is x dot dx plus du over 3 x is 3 minus 2. 3 minus 2. So x dot minus x hat dot is x tutor dot equals to a x tutor x minus x hat bu minus bu on minus L C as far as so a minus L C x. Okay, recall that initially you had x tutor dot equals to a x tutor. Yeah? Without, okay, let me just write down. Without L, without the split back L. Initially, x tutor dot was just a x tutor. And how fast your error goes to 0 is decided by the eigenvalues of A. Yes? Now, x tutor dot is A minus LC x tutor. So, you can change the speed. You can change from the eigenvalues of A to the eigenvalues of A minus LC. So, you can design how fast error will occur to 0 by designing L. Okay? And that's observer design. Alright? Okay? Alright? So, can we move on? You understand it? Yes? No, yes? Alright. Okay? Just a word of caution, you don't have to copy this because you already copied. Alright? Okay? So you can basically feedback the difference between the real output and the estimated output or the mean. You use a state feedback vector L, which is L1, L2, Ln. And the equation is this. So do I have to copy this? Before you copy, I copy it out. So don't copy. Okay? Don't copy, you've already copied. Alright, so basically, estimation error x tutor satisfies x tutor dot equals to A minus LC x tutor. Alright? So provided the model is completely observable, means you can observe all the states of the output. The eigenvalues of A minus LC can be arbitrarily assigned by the choice of L. Okay? Good. So from this equation, what's the characteristic polynomial? Okay, if you only have A, the characteristic polynomial is the determinant of Si minus A. If you have A minus BK, characteristic polynomial is the determinant of Si minus A minus BK. I have A minus LC. It's determinant of Si minus A minus LC. Okay? Alright? So, if you choose L, such that A minus LC is stable, meaning all the eigenvalues are negative and reasonably fast, so they are negative 100, negative 300, then the state error will indicate to 0 and remain there. Alright? So the estimated state will converge to the state, regardless of the initial condition. Okay. Alright, so let's move on to one last part, which is your observer design. Okay, an example. Same example. Okay? For this same example, now you write it in observer canonical form. Okay? Instead of controller canonical form, you write it in observer canonical form. So for observer canonical form, AO is AC transpose. So your coefficients are like the column 1, 0. BO is CC transpose. So what is starts with C, 02 is now 02. CO is BC transpose. So BC is 10, so not 10. Okay? Understand this? No, I've written here. Yeah? Okay, next 2 pages are just for information. How do you do it? Sorry. Are you done? Yes? Say no. Say no. Okay. 5, 4, 3, 2, 1, 0. Okay? Yes. Right. This is just for information. Can you read this on the board? Yes. Okay, this is the question. Question says that the cost of A at -4 and -3. Choose your L, your observable gains. So you get the cost of A minus LC to be at -50 and -60. Okay, so you want the observer polynomial to be S minus -50 as S minus -60. Okay, multiply them out, square plus 50 plus 60, 110S plus 50 times 60, 3000. And I tell you the solution is this. This strange that I wrote K here, right? I'll tell you why later. So if you use Ackermann's formula, that is K. Alright? What you want is L. Theoretically, you can do this. Theoretically. Usually you don't do this in the exam. So if you have post minus 100 minus 1000, your desire is plus 100 plus 1000. You write them out here. Okay, and you compare what you want. A observer with your determinant of SI minus A minus LC. So you compare coefficient for coefficient. Okay, and you find what is L. Okay, this is something that you never do in your exam. So don't do this in your exam. Okay? Alright? Done? Okay? No? What you do is the desired form that polynomial, and then you calculate your determinant of SI minus A minus LC. So these are characteristic polynomial. And then you compare them, coefficient for coefficient. Okay? And then you find what's the L. You never do this in your exam. No, don't do this. What you do in your exam is this. It's something that you also do in MATLAB. So you use Ackermann's formula over again. Like you find K, right? So in MATLAB, what should you do to find L? For L, instead of Ackermann ABP, Ackermann gamma A transpose, because observer is A transpose of AC. Instead of B, you say C transpose. And then polynomial for the observer. But this is only useful in the lab, right? Okay, so now you want to copy. You copy. Take this away, okay? Now you copy this. Usually at this point in time, there are only two types of students. One that immediately starts copying. Before I take this away, the other one that starts at this and actually there's no need to. I'm not quite sure. So for those who don't want to copy, maybe the only useful thing is this one. This one. KO. C. Instead of gamma C inverse, we say gamma O inverse. What is gamma O? Gamma O, instead of B, C is now CO transpose. Instead of AC, BC is now AO transpose CO transpose. Okay, so that's why I find that gamma O is a function of CO transpose and AO transpose. Alright, then you have the polynomial alpha O. Initially you have alpha C AC, right? Now it's alpha O, instead of AC is AO transpose.